Hello, we are Jeonghyuk and Mingyu Park from the Korea Astronomy and Space Science Institute. In this project, we compare the LSTM classifier and a transformer encoder classifier on the A-Genius text classification task. Our goal was not only to compare accuracy, but also to analyze training behavior, generalization, and misclassification patterns. Both models were trained from scratch without using pre-trained language models, and both well evaluated under the same experimental condition. The main goal of this experiment was to fairly compare two different sequence modeling approaches. The LSTM process tokens sequentially, while the transformer encoder used self-attention to model relationship between tokens. To make the comparison fair, we use the same dataset split, pre-processing pipeline, vocabulary, maximum sequence length, and evaluation metrics. We analyze the results using loss curves, accuracy, micro F1 score, confusion metrics, failure cases, and ablation studies. We use the AgNews dataset from Hugging Face. It consists of four classes: Word, Sports, Business, and SciTech. We use 90% of the original training set for training, 10% for validation, and the official test set only for the final evaluation. For pre-processing, all text was lowercase, tokenized, converted into integer indices, and padded or truncated to a maximum sequence length of 128. The vocabulary was built only from the training data with the maximum size of 20,000 tokens to prevent data leakage. We compare two models. The LSTM classifier used an embedding layer, a one-layer LSTM, the final hidden state, dropout, and a linear classifier. The transformer encoder classifier used embedding, sinusoidal positional encoding, two transformer encoder layers, and masked mean pooling, and a linear classifier. Both models use the same training setting. Close entropy loss, Adam optimizer, learning rate is the 1 to the minus 3, batch size is 64, and 10 epochs. These slides show the training and validation loss curve. Both For both models, training loss continuously decreased, which means both models learned the training data. However, their validation loss pattern were different. The LSTM validation loss increased after the middle epochs, showing a clear overfitting tendency. In contrast, the transformer encoder maintained a more stable validation loss. Therefore, based on the loss curve, the transformer showed better generalization behavior. And the next slide shows the accuracy research. Both models improved quickly in the early epochs. However, the LSTM validation accuracy plateaued after the middle epochs, while the transformer encoder maintained a slightly higher validation accuracy. On the final dataset, the LSTM achieved about 91.74% accuracy, and the transformer encoder achieved about 92.26%. The difference was not large, but the transformer showed a slightly better classification performance. And this slide shows the F1 score result. The F1 score is useful because it evaluates class balance performance. The trend was similar to accuracy. The LSTM validation F1 score became stagnant after the middle epoch, while the transformer encoder maintained a more stable validation F1 score. On the, on the test set, the transformer also achieved a slightly higher F1 score than the LSTM. Both models performed best on the sports class, while business and sci-tech were relatively more difficult. This slide compared the confusion metrics. Both models correctly classified most sample, and the sports class was the easiest class for both models. The main error occurred between business and sci-tech. This is because technology-related news often contains business-related words such as companies, market, product, cost, and acquisition, and so on. The transformer reduced some of the business and sci-tech confusion compared with the LSTM, which partly explain its slightly higher overall performance. And these slides show the failure analysis. We divide the error into three groups: LSTM only were wrong, transformer only were wrong group, and both were wrong. LSTM only error often occurred when SciTech article contained many business-related terms. And transformer only errors occurred when certain words such as player or game acted as strong signal for the wrong case, wrong class. And in both wrong case, the text itself was often ambiguous, especially when technology, business, and market-related terms appear together. Overall, the main cause of error were class overlap, limited context, and strong keyword signal. The next slide is the sequence length ablation study. We compared maximum sequence length of 80 and 128 and 256. The question was whether a longer input sequence would improve performance. The research showed that sequence length had only a limited effect. This is because most AG news samples are relatively short, and important information is often located near the beginning of the text. For the transformer, sequence length 128 showed the most stable result, so we consider the 128 is a good balance between performance and efficiency. And this appendix slide show the learning rate sensitivity. Actually, we also did the second ablation with the learning rate, but not included in the report separately because of the limit page, and only briefly during the presentation. We tested the learning rate from to 1 to the -4. Unlike sequence length, learning rate had a large effect on both model. When the learning rate was too large, training became unstable or collapsed. When it was too small, training was stable but too slow within 10 epochs. Overall, the learning rate 1 to the -3 was the most stable and effective setting for both models. Thank you for listening.